These are all functions. If you input things into them, you get things out. Hardly thrilling stuff. But not all of these functions are the same. These ones rely solely on addition and multiplication of both the variables and numbers. These two do not work with solely addition and multiplication and have more meaning, let's say. For example, in a right-angled triangle, sine of x is the ratio of the length of the side opposite to the angle to the length of the hypotenuse. Now that's nice, but gives us a lot of trouble when we try and extend these functions to other mathematical objects. For example, it doesn't intuitively make sense to do sine of some matrix. There's no physical scenario which seems to correspond to this. But a matrix cubed plus 4 times a matrix does make sense, and it is a calculation you can carry out to get some output. And this isn't just true of matrices. One of the key things you can do with mathematical objects is combine them, so there's almost always a defined way of adding and multiplying them. But all of the other stuff, like exponentiation and trigonometry, isn't really that important, so it often isn't defined. But what if we could take these types of functions and turn them into these types of functions, which are, as you surely know, polynomials? Well, it's a good question, and luckily someone else has already come up with the answer. Trying to replicate a function from scratch is quite ambitious, so why don't we start with just trying to approximate one instead? Let's take e to the x and see if we can approximate that. At this point, it becomes useful to consider a function as two separate things. Firstly, as a mapping between one set of numbers and another, and secondly, as a relationship between one variable and another, i.e. something that tells you how your output will change as you vary your input. Looking at e to the x, we can see that it maps the number 0 to the number 1. So we can start building our approximation from the point x equals 0 and say y equals 1. Cool. We now have an approximation which is correct for 0% of the real numbers, which is actually marginally better than our previous 0%. To try and up that percentage even more, we can turn to our second interpretation of a function, a rule which tells us how an output changes as the input changes. We want our approximation to have the same rate of change as the original function, or in fancier terms, we want them to have the same first derivative. If we differentiate e to the x, we get back e to the x. This is arguably the defining property of e, and plugging in x equals 0, we get 1. And so we can update our approximation to 1 plus x, and when we differentiate it, we do indeed get 1 as we were hoping for. Well, we've done the two things we had to, but our approximation is still lacking. What's gone wrong? The answer might be obvious to you, but it's that our rate of change isn't constant. There's a rate of change of the rate of change, and then there's a rate of change of that, and so on and so forth infinitely. So not only does the first derivative have to match, but so do all infinity of them. E to the x is very, very nice in that its nth derivative evaluated at 0 is always 1. So if we want our approximation to improve, we need to add in an x squared term, and this time we can't just write x squared, but have to write x squared over 2, because when you differentiate, you end up multiplying by 2. And then, to improve it once again, we add an x cubed term, x cubed over 6, again with the fraction being there to account for bringing the powers down when you differentiate. And generally, e to the x equals 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4 over 4 factorial, and so on and so forth, which can be written pretty concisely as an infinite series. And this infinite series, which we no longer call a polynomial but instead a power series, isn't just an approximation of e to the x, but it actually is e to the x. And you can do this for all of your favourite non-polynomials. For example, sine x from the beginning is just this, and cosine of x is simply this. And stretching out into generality, a generic Taylor series takes this form here. The things we've been looking at in this video are the special case where a equals 0, when these series are typically referred to as Maclaurin series. Now, when presented logically like this, the fact that Taylor series, which remember were just supposed to be approximations at the start, converge to the original function doesn't seem too crazy. But it's honestly really impressive that this works, because all I gave you was the value of a function and all its derivatives at a single point, and that was enough for you to tell me what the entire function does over the infinity of the reals. This doesn't work for all functions, but it will for the vast majority of them that you've come across. These nice functions are what we call analytic. Or to be slightly more precise, a function is analytic if, at every point on the function, its Taylor series approximation converges exactly to the function for a non-zero interval about that point. This means that something like tan x is analytic, because even though its Taylor series at a given point can't match the entire function, it does work for a non-zero interval around that point. And now it's time to go off on a bit of a tangent into the complex plane to see how what we've looked at can be applied there. If we consider constructing Taylor series, we only need the first derivative, because if the first derivative exists over a region in the complex plane, then all of its derivatives exist there, and it is analytic. Next, we consider using Taylor series. After all, we were doing this to extend the meaning of functions to more mathematical objects. Here, there are two scenarios. Either f of x has no singularities, which are the points where the function is undefined, or it does. If there are no singularities, then we can use our Taylor series to extend the function to the entire complex plane. If there are singularities, then it's a little bit different. We can extend the function outwards in a circle until we hit a singularity, at which point the function is undefined, so obviously we can't extend it any further at that point, but we also can't extend it further anywhere else. So we've failed to extend our function to the entire complex plane. Or have we? Because now we have new values where f of x is defined, and furthermore it is infinitely differentiable because it's just a power series. So we can cook up a new approximation at that point and get a cycle of convergence that covers more and more of the complex plane, and this is one of the ways we can fully extend a function to the complex plane. It's not the only way, and I seriously doubt it's the most efficient way, but hey, it is a cool use of Taylor series. If you enjoyed, don't forget to extend your finger to that subscribe button, and thanks for watching.